Yeah.
Thank you. Yeah, just briefly to touch on myself. So I'm Mischa van Kesteren. I am a solutions engineer at NexGen Cloud. NexGen Cloud have a platform called Hyperstack, which is what I'm going to talk about to you guys today. It is a GPU as a service platform, essentially for on-demand access to GPUs. Um, Sort of true on-demand access. So all of the resources available on the platform are available, within minutes. And as long as you've got the budget, you can utilize as many of the resources as you want at any one time. Um, that level of availability and kind of on-demand and the on-demand nature of the platform, rather than kind of following a more like reserve model where you kind of let us know in advance we're going to need however many GPUs to run our workloads on, has been challenging to implement, and there's some technical decisions we've had to make along the way to reach that point. But a lot of those things that we had to overcome, I felt, made quite an interesting topic for a presentation. So that's what I'm going to talk about today. And hopefully, I think a lot of the lessons that we've learned from doing GPUs at scale are lessons that can also be helpful at any size of machine learning workload, really. Just before I kick off as well, so my background is in high performance computing as well. So, I was designing systems that made use of GPUs for machine learning workloads, 10 years ago when it was still called machine learning and it wasn't called AI. So before I launch into the actual presentation itself, I thought maybe it's worth just having a brief overview of how we got to this place, right? This is a history we all are probably well aware of, but just to set the scene, um, 2021, was it 22? ChatGPT came onto the scene, and all of a sudden, every organization needed some form of AI or some sort of LLM integrated into their business processes, right? And that meant that big money was kind of pouring into this environment. And we still haven't found a better way to train these systems as fast as possible, other than GPUs, right? So there's only one real type of accelerator available. NVIDIA very much the market leader at that time, and I believe still are. And what that meant was that hyperscalers and unicorns, that's really well-funded startups, started hoovering up all of those GPUs. Um, and that caused a challenge, right? And quite a unique challenge, because AI startups, different from previous tech startups, actually need quite a large amount of resource right from day one. And that's quite rare to have a very small company, or there's not even really a company yet, that still needs quite large um, compute resources. But that's where companies such as ourselves or platforms such as Hyperstack entered the picture, right? Because we could offer GPU as a service to these small companies. They can have as much resource as they want for as short or as long a time as they need, right? But that flexibility is essential. But immediately that led us to our kind of first challenge, which is, how do you do that in as fair a way as possible, where you've got multiple people making use of the same platform? And the way that Hyperstack is set up, it's not just multiple users making use of the same platform. Quite often it's users making use of the same host system. So we have a fully virtualized environment, but all of the underpinning systems are all eight GPU systems, but we offer VMs as small as one GPU. So how do we make sure that we can have potentially eight different customers utilizing the same system and not have them interfering with each other? Because the as a service model, the kind of traditional web hosting model, was based on things like oversubscription, where if you've got 10 CPU cores available, you essentially make you virtualize them as 20 cores and assume that the people making use of them aren't going to need 100% of those resources 100% of the time. They might be based in different geographies. Their workloads might be kind of peaky, and just hope that those peaks don't intersect. That works for web hosting and some other kind of more enterprise workloads. But as I'm sure everyone on this call is aware, whenever you try and use hardware to do machine learning, it absolutely pounds every element of the system, right? It thrashes the memory, the CPU cores, the GPUs. So you really can't do oversubscription and expect to have any kind of positive user experience out of the platform. So we needed to make sure that when people made use of our platform, they weren't getting any noisy neighbor scenarios at all. And there's a few different technologies we made use of to enable that. To kind of explain them in a bit more detail, I'm going to rely on this handy block diagram. This is a very simplified view of what the inside of a server looks like. All of our systems and most systems out there are two socket systems, which means they have two CPUs in them. Again, this says Intel Xeon CPUs. We have a mix of CPUs available in our environment. It's just because this was the simplest example I could find of what the inside of a server looks like. It's nice and straightforward. So what you have is two CPUs. Each one's connected to a bank of memory, and each CPU as well has up to 4 GPUs connected to it. In a scenario where you're doing 8 people or 8 users making use of this system, what you really, really need to ensure is that their VM isn't hosted on CPU 1, let's say, making use of memory connected to CPU 2 and GPUs connected to CPU 1 or CPU 2 or a mix of both, because then so much traffic is going over those 3 UPI links in the middle that the performance won't be great. If you add on top of that somebody on CPU 2 doing the opposite, you get all kinds of crosstalk and the performance is really bad. Luckily, there's a technology that exists within processors called non-uniform memory access, or NUMA. And the simplest way to explain this is just that the CPUs understand how long it takes them to talk to different components within the system, specifically the memory. And that means that if we do scheduling, what's called NUMA-aware scheduling, where we provision VMs based on allocations of memory which are local to that CPU, and also crucially for our workload, GPUs that are local to that CPU, performance will be better, and we can also provide reliable performance to customers that are trying to make use of this platform without worrying about crosstalk. And then on top of that, we also pin the CPUs, pin the VMs to the CPU cores to make sure that they don't go walking around inside the hypervisor, basically. But that probably wouldn't happen anyhow. This means that we can provide really high performance multi-tenancy in a secure way. But the lesson I think that we can all take away from this, for us, we obviously learned fairly early on, GPU as a service is not the same as other infrastructure as a service workloads, but also just GPU workloads are not the same as other workloads. So it's always worth thinking, having an understanding of what your host system is, whether it's just your local machine or whether it's a single server running elsewhere or in the cloud. Having an understanding of what the layout of that is and how data flows through it to make sure that it's always optimized for the workload that you have in mind. And on the topic of optimization, you then also need to look at the CPU and the memory, right, that are attached to the GPU. It sounds almost counterintuitive, but actually GPUs don't exist in an island. They are supported by, and essentially what makes them usable is the platform that they're running. If you were to be a kind of a cynical cloud provider and think to yourself, people rent time on the cloud based when it comes to GPU workloads based on GPUs. Okay, so one A100, just compare the cost of one A100 across different cloud providers. Well, I'll do mine much cheaper because I'll just put, very poorly performant CPUs and memory underneath them, but I'll still offer the cheapest A100s. Okay. This really is not workable from a performance standpoint because that CPU and memory infrastructure is acting as a data loader for that CPU. A good illustration of this, if I take you quickly through these two diagrams, what these are is the top one is an example of a typical x86 system with a GPU and a CPU from Intel or AMD. And then the one underneath that is an example of NVIDIA's Grace Hopper environment, where they've got a custom CPU attached directly to the GPU. And also they've got kind of persistent or consistent memory address space across the two of them. That's not particularly important. What is important is that the difference between the top and the bottom one is not the GPU. The GPU is the same between these two platforms. What is different is the CPU it's connected to, the memory it's connected to, and the bandwidths between them all. And what NVIDIA have achieved by changing the things that surround and support the GPU is 1.7 to 2 times speed up on typical training workloads. So it just really makes the point that when you're thinking about the performance of your GPU, also think about the environment around it. And we've all probably been forced to do this as well. When you look at running a particular model or a training or an inference system, and you check what the requirements of it are, you check the VRAM on your GPU, and you think, okay, brilliant, I've got enough memory. You go ahead and try and run the workload, and you get out of memory errors. And it turns out actually there's not enough RAM on the system you're using. So we need to think about the supporting infrastructure for the system as well as just the GPUs themselves. But you also get into kind of then there's the additional area of inter-GPU fabrics. Once you scale beyond a single GPU workload, your GPUs need to communicate with each other. And they can normally typically do this via the PCI links within the system. If you think back to that previous example I showed you, where you had those PCI links connected to the CPUs, and then there was an interconnect between the CPUs. That's the downside of just using PCI links, is that if you're trying to do inter-GPU communication, it's a bottleneck. Also, the bandwidth of PCI is pretty fixed. It's an industry standard. It moves forward one generation at a time, and it doesn't move forward as quickly as GPU technology was evolving, right? So NVIDIA in this instance came up with a technology called NVLink to better interconnect their GPUs. Other manufacturers' GPU interconnects are available. What we found when trying to virtualize this, and it was one of the common problems we come up against, is that we're looking to virtualize cutting edge systems. We're often trying to do things which haven't been done before. Most people, when they buy large scale GPU systems, don't immediately try and install a hypervisor on them, right? They just install them into their massive cluster and use them in a bare metal way. So looking to virtualize them, we often come across challenges where we're trying to do something that's never been done before. The particular case in this instance is because we're using what are called NVLink bridges. Now, NVLink bridges connect together two GPUs to make them function as, or not function as one GPU, but to improve the communication and the rapid speed between those GPUs. As you can see in this diagram here, this is a diagram of like data flow through a system. It's not actually a diagram of a block diagram of the insides of a server, but the kind of what I wanted to highlight with this is that you can see how the bridge works. So it's connecting GPU 0 with GPU 1, and then there's a second bridge connecting GPU 2 with GPU 3, and in a 2-socket 8 GPU system, there's all of this just mirrored on the other side of the server. This is great for VMs or systems which make use of multiple GPUs, or workloads which make use of multiple GPUs. Where the problem arose was that there was no way for us to schedule individual VMs and actually make the hypervisor aware of which GPUs were connected via the PCI bridge, via the NVLink bridge. So we could essentially have been unscrupulous and said, okay, great, we have an NVLink enabled flavor. Here it is, everyone, and there's a price premium for it. But we wouldn't have been able to guarantee that people, unless they were running a workload across all 8 GPUs in the system, that they would actually be gaining the benefit from it. So rather than just walking away and saying this can't be done, we decided, do you know what? We'll just make sure that if people are making use of these NVLink instances, they're making use of them across a whole host system. That way we can guarantee they will be getting the benefit of NVLink. And that was a kind of a real lesson for us as well, that we just need to prioritize the performance of the system and the user experience of the system rather than just chasing kind of latest generation technologies. And that's also a lesson that an individual can take away from it as well, is like, will these latest generation technologies actually benefit me in my workload? And maybe it's not worth the time and effort implementing them if I can't do it in a kind of in a performant and usable way. And we were lucky to find a way that we could in this instance. But that's about scaling workloads within the same system across multiple GPUs. You then also need to think about scaling a workload across multiple GPUs out across multiple systems. At this stage, the interconnect between the virtual machines becomes crucially important, or the interconnect between the nodes becomes crucially important. Unless you're very lucky and you happen to have a workload which is, well, embarrassingly parallel in kind of HPC speak, or I think data parallel is the terminology used in machine learning circles, you're going to need really high inter-node bandwidth. That embarrassingly parallel terminology or data parallel terminology, essentially what that means is if your workload has the characteristic where its performance will scale linearly with the number of nodes you try and run it across. So in this instance, let's say you have a job which takes 10 minutes on one node, it'll take 2 minutes on 5 nodes, and it'll take 1 minute on 10 nodes, right? If that's the case, you're incredibly lucky because implementing a workload across multiple systems is comparatively straightforward, but there are a lot of use cases which don't exhibit these behaviors, and in that instance, you need that high performance interconnect between systems. The challenge that we faced in doing this was that because again we virtualized everything, that virtualization, including the network virtualization, is done by the processor. And as I said earlier, what we want to make sure is that users who are renting CPU cores as well as GPU cores from us also can also make use of sorry, the words escape me right now. Can make use of the full performance of those CPU cores. We don't want to be wasting CPU cycles on network virtualization. So we make use of a technology called SRIOV, right? Doesn't really matter what the letters stand for. What you've got on the left-hand side here is without this technology implemented. You can see you've got two ports, essentially physical ports. That's in the green portion of these boxes. So the green portion is the network adapter in this instance, and the gray portion is the hypervisor, is the host system, and then the white box is the virtual machine itself. So you've got two ports on the network adapter. They get passed through to the host system, to the hypervisor. It virtualizes them. It aggregates them into one single link, and then it passes that one aggregated link to the VM. That's quite a lot of workload for the hypervisor to be doing, right? What we move to with SRIOV and VF lag is a situation where, because of how performant the network adapters are that we use, they do the virtualization of the ports. They aggregate the ports from two into one single port, and then they pass that single virtual interface directly to the VM. So you go from a situation where there's an awful lot of computational work being done on the hypervisor to enable this, and therefore that's impacting CPU performance, to a situation where there's basically none being done by the hypervisor itself, and all of that is offloaded to the NIC. So this way we can really facilitate our customers' needs to do multi-node workloads as well as single node workloads without impacting the performance of the underpinning architecture. And we wouldn't have done this, and we wouldn't have enabled this if we hadn't have thought right from the beginning, people are going to be needing to scale their workloads on our platform, right? People are going to move from single GPU workloads to multi-GPU workloads to multi-node workloads. So I think what we can all take away from this is that right from the start, you should be thinking from an architectural standpoint, not just about, is my current infrastructure performant enough, but also can it scale with me as I kind of develop through the life cycle of my application. The final thing, and sort of uncomfortable reality that I need to talk about slightly as well, is that we realize is that GPUs, just like any hardware, fail, right? And GPUs are running very hot, and they're running constantly. And when you're running infrastructure into the thousands of these components, they are going to break down at times. This will cause workload interruptions as well, and there's kind of and that's what happens. So you need to find a way to mitigate this, okay? And to illustrate this, this is a screenshot taken from Facebook's white paper about their training for Llama 3.1. So they're running at sort of a similar scale, right? Thousands of GPUs, and over a 54-day training period, they experienced, I think if you add all those numbers up, it's over 450 failures, right? So that's almost 10 failures a day. But what I want you to take away from this is not, oh my goodness, GPUs fail all the time. It's that Facebook still successfully completed their training run. And how did they do that? Well, you have to make the right architectural decisions. You have to make sure you design a hardware system that has high availability built into it, from a networking standpoint, from a hardware standpoint, right? Additional kind of availability and reliability features, but then also the way that you architect your workload. Really think about making use of checkpointing, how frequently you checkpoint as well, and what kind of type of storage you're checkpointing to. I've spoken to customers, they're running at very large scale, but their checkpoints are taking an hour at a time. And if they're checkpointing as frequently as you should be, every 4 hours or so is the recommendation, they're essentially using 25% of additional time just to write the checkpoints down. They're still paying for all the infrastructure during that period, so it's a huge waste of resources on your part not to do checkpointing in an efficient and performant manner. But this also flows down to kind of any scale of machine learning where you need to plan for failure on some level, especially if you're working on a local system. If you're just working on a laptop, right? And that's where you're developing your MVP or whatever on. If you're not backing up your data and that system fails, so much of the value of your system and of what you're trying to do and what you have to offer is in your data. If you're you training a brand new model, if you're fine-tuning an existing model, the new thing that you're bringing to the table is the data set, presumably. So it's really important that you protect that data set, that you plan for failure, and you make sure that regardless of what elements of your own personal infrastructure fail, you can recover from that and you can continue on. So that's all I really wanted to talk about today, really. To conclude, infrastructure at scale, as we discovered, is a challenge, but those challenges don't just hit you at scale, they come at any time. But thinking at scale and thinking at those sizes of systems where anything that can go wrong will go wrong allows you to kind of foresee problems that you might come across in your day-to-day. Hopefully, and hopefully some of those things that I've raised today have made you think about that and made you think, okay, yeah, I could take that away. And actually, there's something that I could work on in how I kind of in my current workflow. Or as I said there, you could let someone else worry about it for you who's already faced all these trials and tribulations and make use of their platforms.